Attention is the mechanism that lets a model decide which tokens matter most when building a prediction. The pieces in this chapter move from the simplest form of self-attention to the version used inside large language models. The board now sets out the path, why attention helps, how self-attention works, how causal masking changes it for text generation, and how multiple heads run in parallel to capture different patterns. Attention gives a network a way to focus on the most relevant parts of its input, instead of treating every token equally. That makes sequence models more flexible, especially when long-range context matters. The simplest self-attention computes relationships between tokens directly. From there, trainable weights make the mechanism more expressive, so the model can learn which interactions are useful from data. Causal attention blocks each position from looking ahead, so the model can predict the next token using only earlier tokens. That restriction is exactly what makes autoregressive text generation work. Dropout randomly removes some attention links during training, which keeps the model from relying too heavily on a few connections. The result is usually better generalization on new text. Multiple heads let the model attend to different relationships at the same time. One head might track local syntax, while another follows longer dependencies, and combining them gives a richer representation. Tokenization turns text into manageable pieces, and embeddings turn those pieces into vectors the model can work with. Attention sits on top of that representation. So the next step is to examine the mechanism that connects those vectors to one another. The focus now shifts to attention itself, first as an isolated mechanism, and then as part of a working language model. Studying it separately makes the math and the data flow much easier to understand before the surrounding model parts are added. Track the three-stage structure in the diagram and focus on the second step of the first stage. That is where attention lives, between the input preparation and the larger model code built around it. The diagram places attention inside the early part of the LLM pipeline, before the full model is assembled. That matters because the rest of the architecture depends on this module doing the right kind of token-to-token interaction. The code path starts with a simple self-attention setup. then adds trainable weights, then introduces causal masking, and finally combines several heads. Each variant adds one idea, so the final version is compact but still practical for plugging into the model. Follow the progression across the figure. First, the simplified attention rule, then the learned weights, then the causal mask, and finally the collection of heads. The order matters because each step builds directly on the previous one. The first version shows the basic interaction between tokens. The later versions add the mask for generation and the parallel heads for richer pattern matching, which prepares the ground for the full implementation. Long sequences are hard because the model has to keep track of earlier words while producing later ones. That difficulty is exactly what makes attention useful later on. A sentence in one language often changes word order, grammar, and meaning when it moves into another language. A translation model has to understand the whole sentence, not just map each word to a single equivalent. The important point in the figure is that the source words and target words do not line up neatly. A good translation has to reorganize the message so the grammar makes sense in the new language. That mismatch is why simple word-by-word translation breaks down. The model needs a way to connect each output word to the right part of the input sentence. The standard design splits the job into two parts. The encoder processes the source sentence first, and the decoder uses that processed information to produce the target sentence. Before transformers, recurrent neural networks were the usual choice for this setup. They handle sequences step by step, which makes them a natural fit for text, even though they come with serious limits. The encoder updates a hidden state at every token and tries to squeeze the whole sentence into that final state. Then the decoder starts from that summary and generates the translation one word at a time, using its own hidden state to keep local context. Focus on the flow. The input sentence goes into the encoder ends with one final state, and that state becomes the starting point for the decoder. The whole translation depends on how much meaning survives inside that single compressed representation. This diagram makes the bottleneck clear. The encoder must compress the source sentence, and the decoder has to rebuild the target sentence from that limited information. You can think of that hidden state as a learned vector representation of the input. The problem is that one vector has to stand in for everything the model needs to remember. That single summary causes trouble for longer or more complex sentences. Important details can get lost because the decoder relies on one compressed state instead of direct access to the earlier parts of the input. That limitation is the reason attention was introduced. Instead of forcing everything through one summary, the model can look back at the parts of the input that matter most. Attention helps a model connect each output token to the most relevant parts of the input, which matters most when the sequence is long and the useful information is spread out. An RNN has to squeeze everything it has read into a single state before the decoder uses it. That works for short text, but with longer sequences, details get lost because the decoder cannot directly reach back to earlier words. But now attention changes that bottleneck. Instead of relying on one fixed summary, the decoder can look back at different encoder states at each step and focus on the pieces that matter most for the current output. Track the encoder sequence on the left and the decoder on the right. The important idea is the set of links between them. Each decoding step can draw from different input positions, and those links will later become the attention weights. Those weights act like a relevance score over the input tokens. A large weight means a token contributes more strongly to the current prediction, while a small weight means it matters less for that step. That same idea led to a bigger change. Transformers no longer depend on recurrent layers. They use self-attention so the model can compare tokens with one another directly inside the sequence, which is a better fit for modern language models. Self-attention works within one sequence rather than between encoder and decoder. Each token builds its representation by measuring how relevant every other token is to it, and that interaction is a central part of GPT-style models. The main target now is the attention mechanism itself, because that is the core part that lets the model organize context. Once that piece is clear, the remaining GPT components fit together much more naturally. Follow the flow from each token to the others in the same sequence. The key pattern is mutual interaction. Every position gathers information from all the rest, which is what gives the model a richer representation than a simple left-to-right state. That construction comes first because it explains how the model forms context-aware representations. After that, the remaining parts of a language model can be added on top of a clear attention core. Self-attention is the mechanism that lets a transformer weigh different parts of the same input against each other. And that makes it central to how LLMs build meaning from tokens. The goal here is to understand the mechanism well enough to build it yourself. Once the pieces are clear, the rest of the transformer becomes much easier to read and implement. The word self matters because the comparisons happen inside one sequence, not between two separate sequences. That distinction is the key to understanding what makes self-attention different from older attention models. Each token compares itself with other tokens from the same input, so the model can learn which words, or even which image regions, depend on one another. That internal comparison is what gives the method its name. In sequence-to-sequence models, attention often links an input sequence to a separate output sequence. Self-attention stays inside one sequence and builds context from those internal connections instead. A stripped-down version is the right place to begin because it exposes the data flow without extra parameters in the way. After that, the same structure can be upgraded to the trainable form used in real LLMs. The first version uses plain vector operations, so every step can be checked by hand. That makes the attention pattern easier to understand before any learning is involved. The purpose of this version is clarity, not performance. By removing trainable parameters, the attention scores and the final context vector become direct consequences of the input embeddings. Track the input vectors across the top and the context vector at the bottom. The arrows and weights show how one chosen token collects information from every token in the sequence. The main idea is that every token gets its own enriched representation. For the second token in particular, the model measures how strongly that token relates to all the others and then blends them into one new vector. The sequence is already turned into embeddings, so each position is now a vector rather than a raw word. That gives attention something numeric to work with. Each token becomes a fixed-length embedding vector, and for illustration, those vectors are shown in 3 dimensions. In practice, the same idea works with much larger embedding sizes. A context vector is just the original embedding after it has been mixed with information from the rest of the sequence. That extra information is what lets the representation capture meaning in context. For the second token, the model builds one vector that reflects both the token itself and the influence of every other token around it. That is the practical output of attention for one position. These vectors are what makes self-attention useful for language modeling, because they carry information about relevance and relationship, not just raw token identity. Once trainable weights are added, the model can learn which relationships matter for predicting the next token. A small embedding size keeps the numbers compact enough to inspect on the page. The mechanics are the same no matter how large the real model's vectors are. The input tensor stores one embedding per token, and the second row will become our query vector. With that single sequence in place, the attention computation can start from raw dot products. These scores are the first signal of which tokens relate strongly to the query token. The truncated numbers in the figure are only there to keep the layout readable, not to change the method. Follow the query token on the left and the score values connecting it to every other token. The important idea is that one chosen input vector is compared against the whole sequence one pair at a time. The second token acts as the reference point for the comparisons. Each dot product measures how aligned that query is with one of the input embeddings. Each score comes from comparing the query embedding with one token at a time. They give a single scalar for every position in the sequence. The second row is selected as the query, and then each input vector is dotted with it in turn. The loop writes one similarity score per token into the attention score vector. That line tells you which token is driving the comparison. Everything else is measured relative to that one embedding. These values are still unnormalized, so they only tell you relative alignment. The next step turns them into weights that can be used for averaging. The highest scores go to the tokens most aligned with the query embedding, while lower scores indicate weaker similarity. Those raw numbers become more useful once they are normalized. Dot products are the bridge between vectors and attention scores. Once that connection is clear, the rest of the calculation becomes much easier to follow. A dot product takes corresponding components, multiplies them, and adds the results. In attention, that gives one number that summarizes how well two vectors line up. The loop computes the dot product by hand, one coordinate at a time. The final printout matches PyTorch's built-in version, which confirms the two views are the same operation. The manual multiplication and the library function produce the same scalar, so the formula is doing exactly what the code says. That scalar is the similarity score used by attention. The identical outputs show that the handwritten calculation and the built-in dot product agree. That gives us confidence that the score computation is correct. In self-attention, a larger dot product means the two vectors point in a more similar direction, so the token should receive more weight. That is why the score can be read as a measure of relevance. Raw scores are hard to interpret on their own, so we convert them into weights. Once they sum to 1, the result behaves like a distribution over the input positions. This version divides each score by the total score, so every entry becomes a fraction of the whole. The check at the end confirms that the weights now add up to 1. Focus on the normalized weights rather than the raw scores. The important feature is that the contributions now form a complete set of proportions that add to 1. The normalization step turns comparison scores into usable weights. That makes the next weighted average meaningful and stable. That sum matters because it means the weights behave like shares of attention. Each token now contributes a controlled fraction to the final context vector. These normalized values are easier to interpret than the raw scores because they show relative importance directly. The total of 1 confirms that the sequence has been turned into a proper weighting scheme. Softmax is preferred because it handles large values more safely and gives better gradients during training. It also guarantees that the weights stay positive. This naive softmax exponentiates the scores and divides by their sum. It works for small numbers, but it is not the safest implementation when the inputs get large. The important point is that softmax keeps the same normalization goal while also being more robust. That makes it the standard choice in real models. The softmax output still adds to 1, but now the values are strictly positive and better behave numerically. That is exactly what we want before computing the context vector. Because every weight is positive, each token contributes in a clean, additive way. Larger weights mean larger influence on the final representation. A handwritten version can overflow or underflow when the scores are extreme. The library version avoids those issues and is the safer choice in practice. This uses PyTorch's built-in softmax on the score vector, so the normalization is done in a numerically stable way. The dimension argument tells it to normalize across the entries of that vector. The values line up with the earlier version, which means the stable implementation preserves the same math. The difference is in reliability, not in the final numbers. The built-in function gives the same normalized weights and the same total of 1. That confirms the scores have been converted into a proper attention distribution. The final step is to use those weights to blend the input embeddings into one vector. Each token contributes in proportion to its attention weight, so the result carries context from the whole sequence. The query selects the second token again, and the loop builds the context vector by adding each input vector after scaling it by its weight. That is the weighted average that turns attention scores into representation. That choice keeps the computation tied to the same token we followed through the earlier steps. It is the anchor for the context vector being built here. Follow the weighted arrows into the bottom vector. The size of each contribution matters more than the raw input values now, because the weights decide how much each token adds. The context vector is the output of the attention process for one query position. It mixes the entire sequence into one new representation that depends on the learned or computed importance of each token. The output is just another embedding, but now it has been enriched by context. That is the value self-attention adds to the original token representation. These three numbers are the final context vector for the second token. They summarize the original embedding together with the influence of the whole sequence. The single token case is useful for understanding, but real models need context vectors for every position. The next step is to compute all of them together instead of one at a time. Now the same attention logic is expanded across the full sequence. Instead of one query, every token becomes a query in turn. The method stays the same: compare, normalize, then combine. The only change is that we do it for every row of the sequence, so every token gets its own context vector. Focus on the highlighted row and the repeated pattern across the rest of the table. Each row corresponds to one query token, and each row is normalized separately. The highlighted row is just the same calculation we already did for the second token. The rest of the matrix comes from repeating that calculation for every token in the sequence. The code changes only in scale, not in idea. Instead of one query and one output vector, we build the full attention matrix and then use it to produce all context vectors together. The double loop compares every input vector with every other input vector, producing a square score matrix. Each row holds the scores for one query token against the full sequence. Track the full grid of pairwise scores. The important structure is that every token gets a row of similarities against all tokens, including itself. Adding the extra loop builds the complete table of similarities. That table is the raw material for the normalized attention weights in the next step. These are the unnormalized scores for every token pair. They're symmetric here because each score is just a dot product between the same set of input vectors. Each entry is one similarity score between a pair of input tokens. This matrix is not yet normalized, so the values are still raw dot products rather than attention weights. The figure on the page shows normalized values, but this printed tensor is the unscaled version. Normalization comes right after this and converts each row into weights that sum to 1. The loops are easy to read, but they are slow. Matrix multiplication gives the same result in one compact operation and is the form used in efficient implementations. This single line computes all pairwise dot products at once by multiplying the input matrix with its transpose. It produces the same score matrix as the nested loops, just much more efficiently. The matching output confirms that matrix multiplication and the double loop are doing the same job. The difference is only in speed and compactness. The output is identical to the loop-based matrix, so the vectorized version is correct. That gives us the score matrix we need for the normalization step. Softmax is applied row by row because each row corresponds to one query token. That turns every row into its own distribution over the input positions. The last dimension is the one holding the scores for each row, so softmax turns each row into normalized weights. Every row is handled independently, which is exactly what attention needs. The normalized rows now match the visualized attention weights. Each row tells you how one token distributes its focus across the whole sequence. Each row now sums to 1 and can be read as a distribution over tokens. The second row matches the earlier single query example, which is a useful consistency check. For a two-dimensional tensor, that means softmax runs across each row. So every row gets its own set of weights that add to 1. A quick sum across the last dimension confirms the normalization worked. That check is worth doing whenever you build attention by hand. This snippet checks one row explicitly and then checks the full matrix at once. Both should give 1 because each row has been normalized independently. The result confirms that every row is a proper attention distribution. That means each query token now has its own normalized view of the sequence. The numbers verify the normalization exactly. Every row has become a valid set of weights ready for the final weighted sum. Once the weights are in place, the last step is just a matrix multiply with the inputs. That produces one context vector for each token in the sequence. This multiplies the full attention weight matrix by the input matrix, so every row becomes a weighted mixture of the embeddings. The result is a context vector for each token position. The output still has one row per token, but each row has now been enriched by information from the whole sequence. That is the matrix form of self-attention in action. Each row is a context vector for one token, and the second row matches the single token computation from earlier. That confirms the batch version and the step-by-step version are consistent. The comparison should line up exactly if the matrix approach is correct. Matching that row is the final check that the generalization worked. This printout brings back the earlier single query result, so it can be compared directly with the batch output. The two should be identical for the second token. The match shows that the all-at-once computation preserves the result from the step-by-step method. That is the signal that the vectorized attention code is correct. The repeated numbers confirm the same context vector we computed earlier. With that equality in place, the whole attention pipeline is validated. The basic mechanism now works from end to end: scores, normalization, and context vectors. Adding trainable weights will let the model learn which patterns matter from data, instead of relying only on raw similarity. Trainable self-attention is the mechanism that turns attention from a fixed calculation into a learned part of the model, and that is what makes transformer-style language models adapt to data. Scale dot product attention is the standard form used inside modern LLMs. The important shift now is that the model does not just compare tokens directly. It first learns how to project them into queries, keys, and values. Track the flow from the input tokens into the attention block, then into the context vectors. The diagram separates the learned projections from the later attention calculation, which makes the whole pipeline easier to follow. The earlier version was only a teaching version of attention, but now the mechanism becomes a real neural network layer. After this, causal masking and multiple heads extend the same core idea instead of replacing it. The goal is still the same: build a context vector for one token by mixing information from the sequence. What changes is the route to those weights, because the model now learns how to produce them through parameters. Those matrices are the trainable part of the module, so the attention block can learn which relationships matter. Without learned parameters, attention would stay generic. With them, it can adapt to language patterns during training. The first pass builds the mechanism line by line, so the math stays visible. After that, the same operations get packaged into a class that can plug into the larger model cleanly. The first job is to turn one token into query, key, and value vectors, then use those to compute the attention weights. Once that pipeline is clear, the full sequence version becomes much easier to read. These three matrices are the learned projections that create the three roles in attention. Each input token gets transformed in a different way, because query, key, and value each serve a separate purpose in the calculation. Follow the second token through the three projections. The query comes from the token being focused on, while the keys and values come from the full input sequence. The second token acts as the reference point in this example. Multiplying it by each weight matrix gives three different vectors, and that separation is what lets attention compare meaning and retrieve content independently. The same token was used as the query before, so the structure should feel familiar. The difference now is that the query, key, and value are not taken directly from the raw input. They are learned projections of it. Focusing on one context vector keeps the arithmetic manageable while the mechanism is still being built. Once that works, the exact same steps apply to every token in the sequence. A few small variables make the projection steps easier to read. After that, the matrix shapes will tell us exactly how the attention computation is moving through the data. The first line picks out the second token because indexing starts at 0. The other two lines record the input size and set a smaller output size, so the projection step is easy to inspect. That annotation ties each variable to its role in the computation. The important part is the dimensionality change. The token starts in a three-dimensional space and gets projected into a two-dimensional one. Real GPT-style models often keep these dimensions equal, but a smaller output here makes the matrix multiplication easier to follow. The math is the same either way, only the sizes change. Now, the learned projections get their actual values. These matrices will transform the token embedding into the three attention roles we need for the next calculations. The random seed makes the numbers reproducible, and each parameter becomes a matrix with shape d_n by d_out. The gradients are disabled here only to keep the printout simple. During training, these same matrices would be learned. That flag is only a convenience for this walkthrough. In a trainable model, gradients must flow into these matrices so the attention block can adjust itself from data. Each projection now turns the selected token into its 3 attention representations. Once those vectors exist, the attention score is just a comparison between query and keys. Each line multiplies the same token by a different learn matrix, so one embedding becomes 3 roles. Printing the query first gives a concrete check that the projection has the expected size. The output length follows the number of columns in the projection matrix. Since d_out is 2, the query vector has 2 components. That result confirms the projection worked and produced a 2-number query vector. The exact values are less important than the fact that the token has now moved into the learned attention space. A lot of confusion comes from using the word weight in 2 different ways, so this distinction matters. One set is learned in the model itself, and the other is produced on the fly from the current token interactions. The matrices are the stored coefficients of a layer, while the attention weights are the temporary scores that decide how much each token contributes right now. Keeping those 2 concepts separate avoids a common misunderstanding. That difference is the core idea. Parameters shape how the layer behaves, and attention weights shape how the current example is combined. One is stable across inputs, the other changes from token to token. Even when the focus is one token, the model still compares it against every key in the sequence. That is why all keys and values must be available before the attention weights can be computed. Now the same projection gets applied to the full input matrix instead of a single token. That gives 1 key and 1 value vector per token in a single operation. The full input matrix is multiplied by each learned projection, producing a key matrix and a value matrix. Printing the shapes is a quick sanity check that every token now has its own projected representation. That shape change shows the projection is working across the whole sequence, not just one token. Each row is still a token, but each row now lives in the smaller attention space. Both outputs have one row per token and two features per row. That matches the chosen output size and confirms the sequence-wide projection. With queries, keys, and values ready, the next move is to compare the selected query against every key. Those comparisons produce the raw attention scores before normalization. Focus on the dot product between the query vector and each key vector. That comparison creates one score per token, which is exactly the signal the softmax will later normalize. The key idea is unchanged from the simpler version. Scores measure compatibility. The difference now is that compatibility is computed after the learned projections, not on the raw embeddings. Starting with a single score makes the indexing easy to verify. Once that one value matches, the matrix version should produce the same result in the matching position. The second key is selected with index 1 because Python counts from 0. Then the query and key are dotted together to produce the raw compatibility score for that pair. That indexing rule explains why the second element sits at position 1. It is a small detail, but it matters whenever you map the math notation onto code. Before scaling or softmax, the model has only a raw score. That value still needs normalization before it can act like a useful weight. That number is the raw similarity between the query and the second key. It is not yet an attention weight, only the score that will feed the normalization step. The single dot product scales cleanly to the whole sequence. Matrix multiplication gives every query key comparison at once, which is exactly what makes the implementation efficient. The query is multiplied by the transpose of the key matrix, so one row of scores is produced against all tokens. That transpose is what aligns the dimensions for all pairwise comparisons at once. This row contains one score for each token in the sequence. The individual values should line up with the earlier single score check, which confirms the matrix form is correct. That matching position is the consistency check we want. The same query key pair produces the same score whether it is computed alone or inside the full matrix expression. The second entry matches the earlier scalar score, so the vectorized computation is behaving correctly. The rest of the entries are the query's raw scores against the other tokens. Raw scores can get too sharp as the embedding size grows, so scaling keeps the values in a healthier range before normalization. Softmax then turns those adjusted scores into weights that sum to 1. The key dimension controls the scaling factor, which is the square root of the key size. After that division, softmax converts the score row into a probability-like weight vector across the sequence. Watch the score row shrink into a normalized weight distribution. The purpose of the scaling is to keep softmax from becoming too peaky when the dot products grow large. The notation changes because the meaning changes. Scores are raw comparisons, while attention weights are normalized importance values. That distinction is what lets the later weighted sum behave like a controlled mix of information. At this point, the numbers are no longer raw similarities. They are relative contributions that tell the model how much to draw from each value vector. These values add up to 1 and behave like a distribution over the tokens. The largest entries get the strongest influence in the final context vector. The scaling step is not cosmetic, it stabilizes learning. Without it, large dot products can push softmax toward extremes and make gradients too small to train well. When the raw dot products get large, softmax becomes very sharp and stops passing useful gradient signal. Dividing by the square root of the key dimension keeps the scores in a range where training stays smoother. The name describes the exact computation. Take dot products, scale them, then normalize. The scaling factor is a small adjustment with a big effect on training stability. With the weights ready, the last operation is just a weighted sum over the values. That produces the context vector the token will carry forward. Focus on how the attention weights feed into the values. The weighted sum is the part that turns the abstract weights into an actual output vector. The context vector is the output of the whole attention computation. It keeps the information from a sequence, but it mixes it according to the learned relevant scores. The same weighted sum idea from the simpler attention version still applies here. The only difference is that the weights now come from queries and keys projected through learned matrices. The matrix multiplication applies the weights to every value vector in one step. that yields the context vector for the selected token, which is the output of the attention block. That final vector is the mixture of all values, with the strongest influence coming from the tokens that receive the highest weights. It is the representation the model will use for the focus token. This is the context vector for the chosen token. Its two entries come from the weighted blend of all the value vectors in the sequence. The single token case proves the pipeline works. The same operations can now be applied to every token, so the model gets a context vector for the entire sequence. These names come from information retrieval, and they fit attention very well. Thinking in those terms makes the matching and retrieval roles much easier to remember. Attention borrows its vocabulary from search systems because the structure is similar. One part asks for information, one part stores a searchable descriptor, and one part carries the content to return. The query represents the token we are currently focusing on. It probes the rest of the sequence to decide which pieces should matter most. Each token contributes a key that acts like a searchable description. The query compares against those keys to measure relevance. Once the relevant tokens are identified, the values supply the actual information that gets combined. So the keys decide where to look, and the values decide what to bring back. The same attention pipeline now gets wrapped in a reusable module that makes it fit naturally into the larger language model code later on. The long derivation was useful for understanding, but code in practice should be organized. A class keeps the projections and the forward pass together in one place. This class version follows the same math, but it is ready to reuse. The structure matches the conceptual steps. Initialize the projections, then compute the context vectors and forward. The class inherits from RNN module, so PyTorch can manage it like any other model layer. The constructor creates the three trainable projection matrices, and the forward method repeats the same pipeline. Project inputs, score queries against keys, normalize with softmax, then combine the values into context vectors. Using RNN, module gives the attention layer the standard PyTorch structure for training and integration. That makes the self-attention block behave like a normal layer inside a larger model. The initializer sets up the three learned matrices that drive the whole mechanism. Each one maps the input embedding space into a different attention role. The forward pass is the actual attention computation. It builds scores from queries and keys, normalizes them, and then uses the weights to mix the values. Once the class exists, it can be instantiated and applied directly to the input matrix. That is the point where the math becomes a reusable model component. The seed makes the initialization repeatable. Then the module is created with the chosen dimensions and run on the input sequence. Printing the result gives the full set of context vectors, one row per token. Because the input has 6 tokens, the output has 6 rows. Each row is the context representation for one token after attending to the rest of the sequence. Each row is one context vector, and the second row matches the single token result from before. The gradient note shows that this output is still connected to the computation graph. That match is the consistency check for the whole implementation. It tells us the class version reproduces the step-by-step calculation exactly for the focus token. Trace the input matrix through the 3 learned projections, then into the attention matrix, and finally into the output context matrix. The labels for Q, K, V, and Z mark the full pipeline clearly. The whole mechanism can be read as a pipeline from raw inputs to learn context. The figure compresses the math into one view, and it helps connect the individual code steps to the larger attention flow. The weights are what give self-attention its learning capacity. As training updates them, the model gets better at shaping those query, key, and value spaces for the task. Using RNN, linear gives the same matrix multiplication behavior, but is cleaner and better initialized by default. That makes the implementation more practical without changing the underlying math. This version keeps the same logic but delegates the projection layers to PyTorch's built-in linear modules. The structure is simpler, and the weights are initialized in a way that is usually better for training. The structure is the same as before, but each projection is now a linear layer instead of a manual parameter matrix. The optional bias flag lets the class match the usual layer behavior, and the forward pass keeps the same attention computation. The usage stays familiar because the public interface is the same. Only the implementation of the projection layers changes. The second module is created and run on the same input sequence, but with a different random initialization. That is why its output will not match the first version yet. The numbers that follow are another set of context vectors from the same attention pipeline. They differ because the initial weights differ, not because the mechanism changed. These context vectors come from the same operations, but the initialized parameters are different, so the values shift. The shape and pattern still reflect the same attention computation. That difference is expected because NN, linear, uses its own initialization scheme. Once the weights are aligned, both implementations should behave the same. The task here is to connect the two implementations by matching their weights correctly. The important detail is that one layer stores its matrix in transpose form. If the matrices are copied with the right shape relationship, both classes should produce the same result. That makes the exercise a good check that the two versions are mathematically equivalent. That transpose storage is the main detail to keep in mind when moving weights between the two classes. Once that is handled correctly, the outputs should line up exactly. The attention mechanism is about to gain two major upgrades. One blocks access to future tokens, and the other lets different heads learn different kinds of relationships. Both build directly on the same core computation. Splitting attention into heads lets the model look at the sequence from several angles at once. That usually helps capture richer patterns than a single attention path can manage on its own. Causal attention makes a language model look only at the tokens up to the current position. That restriction is what keeps next token prediction honest, because the model cannot peek at words that have not appeared yet. For generation, each position should be based on earlier context, not on the full sentence. Masked attention enforces that rule by blocking access to future tokens while the model builds its representation. The practical trick is to zero out everything to the right of the current token, then renormalize what is left so each row still behaves like a probability distribution. That gives the model the same shape of attention, but only over valid positions. Track the diagonal in the matrix. Everything above it is future information, so those entries disappear, while each row keeps only the current token and all tokens before it. For the word in the second row, only the earlier word and the current word remain available. That single example captures the whole rule. A token may attend backward, but never forward. The implementation starts from the attention scores we already know how to compute. The new job is to hide the forbidden positions before those scores turn into attention weights. The code will follow the same attention pipeline, but with one extra constraint inserted in the middle. First, we form the scores, then we block future positions, and only after that do we convert the result into weights. Focus on the order of operations. Scores first, masking second, normalization last. That sequence is what turns ordinary self-attention into causal attention without changing the rest of the mechanism. A lower triangular pattern is all we need. If the upper triangle is blocked before softmax, the resulting weights automatically ignore future tokens. Start with the same softmax step used before, because that gives us a row-wise distribution over all positions. After that, the mask will remove the illegal entries. The query and key projections produce the score matrix, and the scaling term keeps the values in a stable range before softmax. At this point, every token can still weigh every other token, so the matrix is still non-causal. That reuse keeps the example short and focused on masking, not on re-deriving the whole attention layer. The attention logic is the same, only the causality constraint is new. These weights look reasonable numerically, but they still allow every row to see the full sequence. That is exactly what needs to change for next token prediction. Every row sums to 1, but nothing is hidden yet. The last columns still receive weight from early positions, which would leak future information if we use these values directly in generation. A lower triangular matrix puts ones on and below the diagonal, and zeros above it. That shape matches the causal rule exactly. Keep the past, block the future. The mask is sized to the sequence length, then filled with ones in the valid region. At that point, the matrix itself already encodes the causal boundary. What matters is the pattern. The diagonal stays open, and everything to the right of it is shut off. That pattern will line up with the attention scores element by element. This matrix is the causal pattern in its simplest form. Multiplying by it will erase every future position while leaving earlier positions untouched. Element-wise multiplication applies the mask directly to the weights. Wherever the mask is 0, the attention score disappears. Wherever it is 1, the score survives. The multiplication keeps the lower triangle and wipes out the upper triangle. The result is still not normalized, but the forbidden positions are already gone. The important change is visible row by row. Future tokens no longer contribute at all. What remains still needs to be rescaled because the row totals have changed. The zeros confirm that the mask worked. For the earlier rows, the total mass is now too small. So the next step is to renormalize what is left. Renormalization restores each row to a valid distribution. Each token still pays attention only to permitted positions, but now the row again sums to 1. The row sums are computed with a column dimension preserved, so division broadcasts correctly across each row. After that, every row becomes a proper probability distribution again. Now the matrix has the same probabilistic meaning as ordinary attention, but only over valid positions. That is the clean causal version we want. The first row now puts all its weight on itself, and later rows distribute weight only across earlier tokens. That is the behavior needed for autoregressive generation. The only subtle point left is why masking before or after softmax does not leak future information. The answer lies in how softmax behaves once mass positions are removed from the distribution. At first glance, it can seem like the masked values still participate in the denominator. But after masking and renormalizing, the effective distribution is the same as if those positions had never been allowed in the first place. Softmax only matters over the entries that remain active. Once a position is forced out, it contributes nothing meaningful to the final attention weights. That is why there is no leakage. The model behaves as though it had only ever seen the permitted tokens when it formed the weights. There's a cleaner way to do the same job. If mask scores are set to negative infinity before softmax, the exponent becomes 0 and the unwanted positions vanish automatically. Watch the difference in placement. The mask now acts on the scores themselves, not on the already normalized weights. That saves a step and gives the same causal result. The diagonal rule stays the same, but the implementation becomes simpler. Instead of zeroing weights afterward, we remove invalid scores before the probability calculation starts. Softmax turns large negative values into values so close to 0 that they contribute nothing. Negative infinity is the extreme case, and it cleanly forces the probability to 0. The upper triangle marks the forbidden future positions. Replacing those entries with negative infinity means the softmax will ignore them without any extra normalization step. The mask is built above the diagonal. Then mask_fill inserts negative infinity wherever the Boolean mask is true. That prepares the score matrix for a single softmax pass. The score matrix now contains valid numbers only where attention is allowed. Every forbidden cell is already marked, so softmax will erase it automatically. The future positions are now literally absent from the score matrix. Once softmax sees these values, those entries collapse to 0 probability. At this point, the computation is complete in one step. Mask scores go in, causal attention weights come out. No separate renormalization is needed because softmax handles it for us. The scaling stays in place, and softmax now runs over a matrix where illegal positions are already impossible. The output will match the earlier masked result, just with less work. That confirms the shortcut works. The distribution is still valid, and the masking rule is preserved exactly. The numbers match the earlier masked distribution, which shows the two approaches are equivalent. The second method is just more efficient. Once the weights are correct, the rest of attention works exactly as before. Multiply by the value vectors to get context. Before doing that in a full model, there is one more regularization detail to add. Dropout adds another layer of regularization on top of causal masking. The goal is to keep the attention mechanism from depending too heavily on any single weight pattern during training. Dropout works by randomly dropping some activations while the model trains, which forces the network to spread information more broadly. It is turned off when the model is used for inference. In attention layers, dropout is usually applied after the weights are formed. That means some attention links are removed during training, which makes the model less dependent on any single connection. Compare the causal mask on the left with the extra dropout mask on the right. The first enforces the autoregressive rule, and the second adds training time noise for regularization. The two masks serve different jobs. One protects the future, and the other randomly removes some remaining attention to reduce overfitting. With a 50% rate, roughly half the entries are dropped each time. The remaining values are scaled up so the average magnitude stays consistent during training. A fixed seed makes the random mask reproducible, and the example uses a matrix of ones, so the dropout effect is easy to see. The surviving entries get doubled because this is training time dropout. Those two notes explain the setup. The rate controls how many values disappear, and the all ones input makes the risk scaling visible immediately. The pattern is random, but the overall effect is predictable. Some entries vanish, and the remaining ones are amplified to compensate. The surviving values are doubled, which is the standard scaling used by dropout during training. That keeps the expected sum roughly stable, even though some entries were removed. That scaling is the reason dropout does not shrink the layer on average. It preserves the training time balance, so the model behaves consistently when dropout is turned off later. The same mechanism can be used directly on attention weights. During training, some connections are removed before the values are mixed into the context vectors. Using the same seed makes the mask reproducible again, this time on the attention matrix. The surviving attention entries will be scaled, just like in the simple example. The causal structure stays intact, but some of the remaining links are dropped too. That adds regularization without changing the basic attention rule. Some rows lose nearly all their mass, while others keep a few connections and scale them up. That randomness is exactly why dropout helps the model avoid brittle dependence on one pattern. The exact random pattern may differ a bit between platforms, so matching every value byte for byte is not the important part. The important part is the mechanism, random removal plus scaling. With masking and dropout in place, the attention layer is ready to be packaged into a reusable module. That module will become the building block for multi-head attention. The class collects the masking logic, the dropout step, and the projection layers into one clean implementation. It is the version that will be used as a foundation for the larger attention modules later on. The new class extends the earlier self-attention module rather than replacing it. That keeps the design familiar while adding the two features needed for GPT-style modeling. The class also has to work on batches, not just on one sequence at a time. That matters because training uses many batches, and the attention code must preserve the batch dimension throughout. A duplicated example gives us a simple two-item batch without changing the underlying token content. It is a quick way to test whether the tensor shapes line up correctly. Stacking along dimension 0 creates the batch axis. The result is a three-dimensional tensor: batch size, sequence length, and embedding size. That shape means there are two separate sequences, each with 6 token vectors, and each vector has 3 features. The attention layer must process all of that at once. This is the standard layout for batch transformer input. The first axis is the batch, the second is time, and the third is the embedding representation. The shape confirms the batch test worked. The layer now has to produce a matching batch of context vectors with a new output size on the feature axis. The structure is still the same attention layer, but with two crucial additions. One prevents future leakage, and the other regularizes the learned weights during training. The listing pulls the ideas together in one implementation. Pay attention to the buffer for the mask, the in-place masking in the forward pass, and the dropout on the normalized weights. The linear layers build queries, keys, and values in the usual way. Then the registered mask blocks future positions inside the forward pass. After softmax, dropout thins the attention weights, and the final matrix multiply produces the context vectors. Each note highlights a design choice. Dropout regularizes the weights. The buffer travels with the model to the right device. The transpose preserves batch first layout, and the underscore means the masking happens in place. That buffer is not a trainable parameter, but it still belongs to the module. When the model moves devices, the mask moves with it, which prevents device mismatch problems during training. Once the class is defined, it behaves like the earlier attention module from the outside. The difference lives inside the masking and dropout logic. The batch goes through the new attention module, and the output preserves the batch and token axes while changing the feature size to the _out. That confirms the class is wired correctly for batched inputs. The output feature size matches the chosen output dimension, so every token gets a new learned representation. The attention layer has turned the sequence into context-aware vectors. The shape tells the story clearly. 2 sequences, 6 token positions, and 2 features per token in the output. That is exactly the batch context tensor we wanted. The essential pieces are now in place. Masking for causality, dropout for regularization, and a batched implementation that fits the training pipeline. The next step is to run several of these attention paths in parallel. Follow the progression from simple attention to trainable attention, then to causal attention. The final box prepares the way for multiple attention heads working side by side. The sequence of upgrades matters. First, the mechanism learns weights, then it obeys causality, and finally it scales into multiple heads. That final form is what the model will use. Single-head attention gives one way of focusing on the input, but multi-head attention lets the model learn several different patterns at the same time. That extra capacity is a big part of why transformer models handle language so well. The goal is to take the causal attention module already built and expand it so several heads can work together. Multi-head attention is the standard form used in transformer models. Each head learns its own attention pattern, so one head can focus on one kind of relationship, while another head learns something different. A single causal attention module has only one set of weights, so it can only form one view of the sequence at a time. There are 2 useful ways to think about the implementation. Start with the intuitive version by stacking separate causal attention blocks. Then move to the more efficient version that does the same work with one integrated module. The first implementation path is very direct. Build several self-attention heads. give each one its own parameters, and combine their outputs. That makes the idea of multi-head attention easy to see before the optimization comes later. Each head is a separate copy of self-attention with different learned weights, so the heads do not all make the same decisions. The cost is higher, but the benefit is that the model can capture more complex patterns across tokens. The diagram groups several single-head modules together and then merges their outputs. The important idea is not the drawing itself, but the fact that each head processes the same input through a different learned projection. Focus on the repeated attention blocks and the separate value, query, and key weights inside each one. The stacking makes the parallel structure visible. Several heads work independently. Then their context vectors are collected together. With two heads, each head produces its own context vectors, and those two results are concatenated into one larger representation. The same pattern applies to the query, key, and value projections, not just the values. The heads differ because each one uses its own linear projection of the input. In code, the simple wrapper class makes that idea concrete by creating several causal attention modules and joining their outputs at the end. The wrapper class keeps the implementation simple. One list of heads, one forward pass, and one concatenation step. That makes the logic easy to follow before switching to the more compact version. The constructor builds a module list of causal attention heads, so each head has its own parameters and can learn a different pattern. The forward method runs every head on the same input and concatenates the results along the last dimension, which is how the separate heads become one combined context vector. If each head outputs two numbers and you use two heads, the final representation has four numbers per token. That is the basic shape logic of multi-head attention. The heads add their output dimensions together. Track the two separate context vector blocks and the way they line up side by side. The key relationship is that the columns from both heads are concatenated to form one wider embedding for each token. The figure makes the dimensionality change concrete. Each head contributes its own columns, and the final embedding is just the two head outputs placed next to each other. The The wrapper is used the same way as the earlier attention modules, so the interface stays familiar. The only thing that changes is that the output now contains one block of features from each head. The batch is passed through a two-head wrapper with an output size of 2 per head, so the combined representation has 4 features per token. The printout at the end is the quickest way to confirm that the concatenation step is working exactly as intended. The tensor shows 2 identical batch entries because the input texts were duplicated. The important part is the shape. 1 batch axis, 1 token axis, and a wider feature axis created by the 2 heads. The result confirms the expected shape. 2 sequences, 6 tokens each, and 4 features per token. The identical values across the 2 batches come from the duplicated input, while the last dimension reflects the 2 heads joined together. The 3 dimensions mean batch size, token count, and embedding size. That embedding size is 4 because 2 heads each contribute 2 features. The challenge now is to keep 2 heads, but make the final representation only 2-dimensional. That means the total output width must shrink, even though the number of heads stays the same. The class does not need to change for this one. Only one of the dimensions passed into the constructor has to be adjusted so that the 2 heads still exist, but their combined output is smaller. The wrapper version is easy to understand, but it repeats the same matrix multiplications for every head. A more efficient implementation computes the projections once and then splits them into heads afterward. The second implementation keeps the same idea, but organizes the computation around one larger set of projection weights. That lets the model process all heads together instead of one by one. The wrapper approach built multi-head attention by combining several separate attention objects. It works well for understanding the concept, but it is not the most efficient way to run the model. A single class can hold the whole multi-head mechanism, including the projections, the splitting, and the final combination. That avoids keeping 2 separate implementations in sync and makes the computation tighter. The integrated version starts with one linear projection for queries, keys, and values, then reshapes those tensors into separate heads. After attention is computed, the head outputs are merged back into one tensor. The code is worth studying line by line because the tensor shapes do the real work. The class looks more compact than the wrapper, but the core idea is still the same multi-head attention mechanism. The next class combines the logic of projection, splitting, masking, attention, and recombination in one place. The main benefit is that it computes all heads in a batched way. The class first checks that the output size can be divided evenly across heads, then defines one projection each for queries, keys, and values. After the linear layers, the tensor is reshaped into head dimension blocks, transposed so heads become a separate axis, and used in batched matrix multiplication before the outputs are flattened and pass through the final projection. These notes trace the shape changes through the whole method. The main pattern is simple. Project once, split into heads, compute attention per head, then merge everything back into the desired output width. Even though the tensor reshaping looks heavy at first, the method is still doing the same multi-head attention work as the wrapper version. The difference is that the repeated linear work is consolidated into one implementation. The wrapper starts with separate heads and combines them afterward. The integrated class starts with one projection and then splits that result into heads internally, which is why the tensor operations look reversed. Focus on the top and bottom halves of the figure. The top builds separate query matrices for each head, while the bottom builds one larger query matrix and then splits it into head-specific parts. The visual comparison makes the efficiency gain clear. Instead of repeating the same projection for every head, the integrated version computes one projection and slices it into the pieces each head needs. The splitting happens through reshaping and transposing, not by creating separate modules. Once the query, key, and value tensors have the right shape, batched attention can run across all heads together. The central trick is to factor the output width into two parts: the number of heads and the size of each head. That is why the code requires the output dimension to be divisible by the number of heads. After reshaping, the head axis is moved in front so each head can be processed as a batch. That layout is what makes the matrix multiplications line up cleanly across tokens and heads. A small tensor makes the batched multiplication easier to see. The same operation is applied independently to each head, even though it is written as one compact expression. The tensor is shaped as one batch, two heads, 3 tokens, and 4 values per token. That matches the layout produced after the reshape and transpose steps in the attention class. That shape means one example in the batch, 2 heads, 3 tokens, and 4 features per token inside each head. The dimensions match the structure the attention code expects before the matrix multiplication. The multiplication uses the last 2 dimensions as the matrix axis and leaves the head axis untouched. That is why the same line computes a separate token-by-token score matrix for every head. This line multiplies each head's token matrix by its transpose, so the token dimension lines up against itself. The result is 1 score matrix per head, computed in a single batched operation. The output confirms that batched multiplication is doing the work of 2 separate matrix multiplications at once. Each head gets its own 3 by 3 result. The first 3 by 3 matrix belongs to the first head, and the second 3 by 3 matrix belongs to the second head. That is exactly what we expect from a batched operation over the head dimension. PyTorch treats the last 2 axes as the matrix dimensions and repeats the multiplication across the remaining leading axes. That makes the code short while still preserving a separate computation for each head. The same result can be written more explicitly by selecting each head and multiplying its token matrix by its own transpose. The compact batch form and the explicit per head form give the same answer. This version pulls out the first head and the second head separately, then multiplies each one by its own transpose. Is the manual version of the batched operation, useful for checking that the compact syntax is doing the right thing. The 2 explicit head computations match the batched output exactly. That confirms the tensor layout and the multiplication logic are both correct. The first and second heads produce the same score matrices that appeared in the batched result. That confirms the batched expression is just a compact way to do the same per head work. After attention is computed, the head outputs are moved back to token major layout and then flattened into 1 vector per token. That is the step that recombines all heads into a single representation. The output projection sits after the heads are merged, so it can mix information across the concatenated features. It is not strictly required, but it is common in transformer-style attention blocks. This is where the efficiency gain comes from. The integrated class computes queries, keys, and values once each, instead of repeating those expensive matrix multiplications for every head. The math is the same, but the work is organized much better. The integrated class is used just like the earlier attention modules, so it drops into the same workflow. The difference is that it returns the combined multi-head representation directly. The model is created with 2 heads and an output size of 2, so the final tensor should keep 2 features per token. Printing the shape confirms that the integrated class honors the requested output width. The output dimension is not determined by the number of heads alone. It is set by d_out, which controls the final embedding size after the heads are combined. The output now has shape 2 by 6 by 2, which means each token ends with a 2-dimensional context vector. That shows the final width is coming from d_out, not from the number of heads alone. The efficient class is the one to keep for the full language model, because it gives the same behavior with cleaner and faster computation. Small dimensions were chosen here only so the tensor values stay readable. Real GPT. 2 models use much larger settings. The small model uses 12 heads and 768 dimensional context vectors, while the larger one uses even more heads and a wider embedding. In GPT models, the input and output embedding sizes match, so d_in equals d_out. The final practice is to set the attention module up with GPT-2 size dimensions. Matching the head count and embedding width helps connect the small example code to the real model configuration. Use the same class, but choose the GPT-2 settings: 12 heads, 768 input dimensions, 768 output dimensions, and the appropriate context length. The key is that the dimensions must fit the class constraints while matching the model size you want. Attention ties the whole sequence together by letting each token gather information from the rest of the input. The main idea is that a token does not have to rely only on its own embedding. It can build a richer representation from the surrounding context. Each input element is transformed into a new vector that carries information from other positions as well. That is what makes attention useful. The representation at one position can reflect the broader sentence or sequence. The mechanism builds that new vector by taking a weighted sum across the input vectors. Tokens that matter more for the current position get larger weights, so the output emphasizes the most relevant parts of the sequence. In the simplest version, similarity between vectors is measured with dot products. A larger dot product means the vectors point in more similar directions, so the model gives that input a stronger weight. That operation is just multiplying matching entries and adding the results. It is a compact way to turn two vectors into one number that captures how aligned they are. When these calculations grow large, matrix operations let us do the same work in a cleaner and faster form. Instead of writing many loops by hand, the whole batch of dot products can be carried out together. In transformer models, the inputs are first projected into queries, keys, and values. Those trainable matrices let the model learn how to compare tokens and how to build the final context vectors from the most relevant values. For left-to-right text generation, a token must not see words that come later in the sequence. The causal mask enforces that rule by removing attention to future positions, which keeps the prediction process valid. A dropout mask adds noise during training by turning some attention weights off. That makes the model less dependent on any single path through the network and helps it generalize better. Using several attention heads lets the model look at the same sequence in different ways at the same time. One head may focus on syntax, another on long-range meaning, so the combined result is more expressive. A direct implementation just runs several causal attention modules side by side and combines their outputs. That matches the idea well, even if it is not the most efficient form. The more efficient implementation groups those head computations into batched matrix multiplications. That way, the model processes many heads together and uses the hardware much better than separate loops would.